So in this video, I'm going to discuss about this factors which are affecting the stability of conformers. This particular topic has been pulled out from the degree first semester syllabus, that is Alicyclic Hydrocarbons, that's chapter 6. The whole chapter has been discussed on my YouTube channel. If you like it, please do like, share and subscribe my channel. So before understanding the factors which are affecting the stability of these conformers, let's understand what is the concept of conformation first. So these conformational isomers, which are nothing but the conformers, also called as conformers, are nothing but the isomers which are having the same bond connectivity sequence. That means the sequence is not changed in the molecule. Only thing is they can be interconverted by the rotation around the single sigma bond. So for example, if we take this cyclohexane here, so there's different conformations which are possible for this cyclohexane. A few of them has been shown here. The first one is a planar conformation, second one is a chair conformation, and the third one is a board conformation. Now, if you see this closely, this can be, I mean, these three conformers can be interchanged just by the rotation of these sigma bonds here. So there is no connectivity change. That means the carbon atoms are arranged in the same sequence. Only thing is the sigma bonds are rotated in different manners so that the most stable conformation is reached. That's it. So the factors which are affecting these conformers are four here, four factors. The first one is the angle strain. Second one is the torsional strain. Third one is the van der Waals strain. And the fourth one is the dipole-dipole interaction. So let's understand each of them in detail. The first one is the angle strain. So we know that any sp3 hybridized carbon atom. Now, for example, I've taken this sp3 hybridized carbon atom, for example, the methane, the simple molecule, where the carbon here is having a tetrahedral geometry, nothing but the bond angle here is 109 degrees 28 minutes. So any deviation from this tetrahedral angle in the sp3 hybridized carbon atom will lead to a strain in the molecule, which is called as a bond angle strain or the angle strain or the Bayer strain. So any deviation from this ideal bond angle, this bond angle is also called as ideal bond angle, or the ideal value will result in the strain in the molecule, which is nothing but the angular strain. So we can explain this as an increase in the potential energy of the molecule because of the deviation from this ideal bond angle, that is 109 degrees 28 minutes. So it can be best understood with the help of the example, that is a cyclopropane, where the three carbon atoms have been arranged in a cyclic manner where the bond angle is only 60 degrees here. So if you see the bond angle here, actual cyclopropane is having the 60 degrees bond angle, but the expected one is 109 degrees 28 minutes. But here it is having a bond angle of 60 degrees. So this deviation from the tetrahedral bond angle or the ideal bond angle, which results in the severe strain in the molecule, which is nothing but the angular strain. So this angular strain is also seen in some other examples. The first one is a cyclopropane, where we have already seen that the ideal bond angle or the expected one is 109 degrees 28 minutes and the actual is 60 degrees. So when we subtract this, we can get the deviation from this bond angle, which is nothing but the angle strain. And when a cyclobutane, if you take the angle which is seen as 90 degrees but the expected one is 109, so the deviation is 19 degrees, 19.5 degrees. And in cyclopentane, so the deviation is only 1.5. So this is what is angular strain. And let's take this torsional strain. This is a second type of strain which is affecting the stability of the conformers. So this torsional strain can be best explained with the help of an example. Let's take this, uh, I mean, sorry. Yeah. So this torsional strain can be best explained with the help of an example. That's ethane molecule, which is a substituted ethane here. So when we look at this Newman projection formula of this particular molecule, these two chlorine atoms are in eclipsed conformation. So this is an eclipsed conformation where the two chlorine atoms on the two carbon atoms here, this is one carbon and the back one is this carbon. So the two chlorine atoms on the two carbon atoms are suffering from this eclipse strain where the two chlorine atoms are just one behind the another. So there is a strain in the molecule which is nothing but the torsional strain or the eclipse strain. But it can relieve from this torsional strain by just rotating one of the carbon atoms by 180 degrees, and then will reach at the staggered conformation where it is relieved from this torsional strain, where these chlorine atoms on the two chlorine atoms, I mean two carbon atoms, are now or not in eclipsed conformation, that is not one behind the another, but at a safe position where they're not suffering from strain here. So they're free from strain. So we can now explain this torsional strain as the any deviation from this staggered conformation or the staggered arrangement of a molecule will result in the torsional strain, or this is also called as a pizza strain in the molecule. So any deviation from this staggered conformation, now this is the staggered conformation, will result in this torsional strain here. So we can now explain this as um, yeah, the same thing where the tetrahedral carbons will having a staggered conformation will be more stable when rather than when they are in the eclipsed conformation. Yes, this is what is torsional strain, and this can be best example explained by means of this cyclopropane again, where when we take these two hydrogen atoms on the two carbon atoms, now they are one behind the another. The hydrogen atoms here are suffering from the eclipse strain here. So there's nothing but the increase in the potential energy of the molecule uh, because of the, yes, it is that the is the increase in the potential energy of the molecule because of the repulsion in between the electrons that do not share an atom. So on the different atoms, these electrons are present, but they are uh, the facing these repulsions, and thus will result in the increase in the potential energy of the molecule, resulting in the instability of the molecule. Now, the third one, which is affecting the stability of the conformers, is nothing but the van der Waals strain. Um, so now this van der Waals strain can be best explained with help of an example again, that is the um, cyclohexane here. Now, when we take this cyclohexane here, these two hydrogen atoms on C1 and C5 carbon atoms here are facing this repulsion, which is also called as steric repulsion because of the arrangement of this methyl group on this and the hydrogen on this. So if these two hydrogen atoms are just close to each other, uh, just close to each other, that is less than this van der Waals radii, then this is affecting, I mean, this is suffering from this repulsion that is called as an steric repulsion. So this van der Waals radii is nothing but is the radius uh, So this van der Waals radius is nothing but the radius around the atom less than which it will suffer from the repulsion. So if these two hydrogen atoms, if they are brought closer than lesser than this van der Waals radii, then they will suffer from repulsion. So in the same way, these two hydrogen atoms on the non-bonding atoms, that means these two are not bonded to each other, they are on the different carbon atoms. So this is C5 and this is on a different carbon atom. They are suffering from the repulsion, which is nothing but the van der Waals repulsion or steric repulsion. So this methyl group is in eggshell position now. So now when this methyl group is brought to a different position, that is an equatorial position, then it will relieve from this strain that is nothing but the van der Waals strain. So this can be defined as this van der Waals strain or the steric strain is increase in the potential energy of the molecule, because which is arising because of the repulsion in between the electrons that are not directly bonded to each other. So this is because of the repulsion in between the electrons in an atom which are not directly bonded to each other. So if these two non-bonded atoms are uh, brought anything closer than this van der Waals radii will suffer from repulsion, otherwise they attract each other. So this particular strain which is arising because of this crowding is called as a steric repulsion or van der Waals strain. So yeah, the fourth one is the dipole-dipole interaction. So the fourth type of strain which is affecting the stability of this conformers is nothing but the dipole-dipole interaction. So let's understand what are these dipoles first. Molecular dipoles. Let's take an example of this HCl, which is a simple molecule. Let's take this, which are sharing a covalent bond in between these two. And we know that the chlorine is more electronegative than hydrogen. Because of this more electronegativity of this chlorine, it's tried to attract the electrons more towards it. So as a result of this, it will get a partial negative charge. And because this hydrogen is less electronegative, so it will attain this partial positive charge. So I'll show this like this. This is a partial negative and this is partial positive charge because of the electronegativity difference here. So we can see this electron density is now around this chlorine atom. So there's a dipole which is created in the molecule. The name itself suggests dipole. That means two poles are created in the molecule. There's a positive charge and the negative charge because of this unequal sharing of this covalent bond or the unequal sharing of this pair of electrons in between the H and Cl in the example I'm taking. So there is a dipole which is created in the molecule, which is so the molecule is now is said to be polar here. So uh, so this one is polar here. This is what is molecular dipole, because one side of a molecule is getting a partial negative charge and the other side of a molecule is getting a partial positive charge because of the electronegativity difference here. So when we take up the example of this CO2 here, we know that oxygen is more electronegative than carbon, and so this is getting the partial positive and these two ends of a molecule are getting the partial negative charge. But because of the geometry of this CO2, we know that it's a linear geometry. The two dipoles are cancelling each other, so there is no net dipole moment. The dipole moment is zero here because of this geometry. So the dipoles are cancelling each other because they are pointing in the opposite directions. So this is no net dipole moment here. But when we take the example of HF here, we know that this fluorine is highly electronegative than hydrogen, so this is gets a partial negative charge here, and in the same way this is getting the partial positive charge here because hydrogen is less electronegative. And now this is said to be polar here, and there is a net dipole moment here. uh, so the molecule having a dipole, and they put that because there is no opposing dipole moment here and there is no opposing dipole moment to cancel each other. So this particular example is said to be polar here. But the other example which we have seen, that is CO2, is not polar because there is a cancellation of this dipole moment where the net dipole moment is zero. Now let's take now understand what is this dipole-dipole interaction. As we've understood the concept of what is a dipole, now understand what is this dipole-dipole interaction. So we know that this is a covalent bond and this is also covalent bond. So the molecules will align in such a way that now it will be more stable. That means the positive end of one molecule will try to get attracted to the negative end of the other molecule because of this permanent dipole in the molecule, that is a HCl is permanent dipole, and there is a certain sort of this intermolecular bonding which is created here, which is nothing but this intermolecular attraction. So this is a sort of this intermolecular attractions because of this permanent dipole in the molecule. So the negative end of one molecule will get attracted towards the positive end of another molecule. This is nothing but this dipole dipole interaction here. Yes. Now uh, yeah, I've already said this now. This is intermolecular attraction, which is attraction in between the molecules because of the permanent dipoles which are created in the molecule here. Yes, and when we take the example of water molecule here, there's a permanent dipole here because oxygen is more electronegative, and because of the geometry of this, it is having the net dipole moment, and there's a sort of I mean, there is hydrogen bonding or intermolecular attraction in between the two molecules, and this is nothing but the dipole-dipole interaction here. And the same example I've taken here, I've already explained this, that is the HCl. There is an intermolecular attraction in between the negative end of one molecule and the positive end of molecule is nothing but the hydrogen bonding. Yes. So now we can explain this as a molecule which takes the conformation or the position which will result in the dipole-dipole interactions, more favorable dipole-dipole interactions, that is to maximize the dipole-dipole attractions and to minimize the dipole-dipole repulsions. That means the molecules will align in such a way to minimize this dipole-dipole repulsions and to maximize the dipole-dipole attractions. So these are the four factors which are affecting the stability of this conformers, but the net stability of the molecule is determined by combined effect of all these four factors. It doesn't depend on only one factor, but all these four factors will determine the stability of this uh, molecules. Sometimes, for example, if you take sometimes a molecule may accept the angle strain to relieve from van der Waals strain or dipole-dipole interactions. So there can be a little more of angle strain it accept to relieve from this van der Waals strain, or that for that matter torsional strain or dipole-dipole interaction. So these are the four factors which are affecting the stability of the conformers here.